Here's a center of mass problem that leads to polar coordinates for a double integral. The region is, it says the boundary is the semicircles y equals root 1 minus x squared and y equals root 4 minus x squared, together with the portions of the x-axis that join them. So it's between the upper semicircles, centered at the origin, of radius 1 and 2, is what it really means. And so let's just go ahead and graph, just so I can point to something. X squared plus y squared equals 1. Let's plot that implicitly. Now that's going to graph the whole circle. And it's going to make it look like an ellipse until I change the scaling a little bit. Let's say 2.5 by 2.5. And let's add an item, x squared plus y squared equals 4. Okay, so we just have to remember it's the upper half of that. Now it's very important it's the upper semicircle portion of the annulus, the ring here, because if it was the whole thing, well, let's see. First, let's look at what the density is. The density function, it's proportional to the distance from the origin. That's otherwise known as r. Okay, so in other words, rho of xy is really better thought of as rho of r, or well, I guess we can say r theta, but it doesn't have a theta. It's equal to kr. And we can just choose whatever that proportionality constant, whatever letter we use, and it's going to come out in the wash for a center of mass calculation. Now, if this were the problem and it was the whole annulus, by symmetry, immediately we could say it's 0. Not just because of the picture, but because of the picture and the fact that the density doesn't depend on the direction. So all the mass up here and all the mass up here, the y coordinates will cancel out and give 0. The x coordinates will cancel out and similarly give 0. Since it's the upper semi-annulus, the y coordinates will definitely not cancel out and give 0. The x coordinates will, however, though. So just by symmetry, by looking carefully at the symmetry, x bar is going to be equal to 0. X bar equals 0. Okay, and now we need to find y bar. Well, first we need to find the mass. So the mass, with only two s's, m is going to be, by definition, it's the integral over the whole region, which is 0 to pi, and then 1 to 2. So remember, it's the stuff in here where r goes from 1 to 2. As the radar beam sweeps around, it's going to not have anything to do with anything with r is 0 to 1, but 1 to 2 it is going to have. It is going to intersect the region. Okay, so then that's just going to be rho of r dr d theta. And remember, the r is because this is dA. R dr d theta, that package, that whole package is d theta. And this should have been a pi. I'm sorry. I said pi and I wrote down theta. Okay. So that's going to be, well, I'll just copy that sucker. Rho of r is kr. And so that's going to be a kr squared. Okay. And now this is the kind of thing that has nothing to do with theta. And so that's just going to come out as a pi. And then a k is going to come out. And then the integral of r squared is r cubed over 3. And so we're going to get r cubed from 1 to 2. Let's put an equals here. And so that's going to be pi k over 3, and then times 7. Okay, so 7 pi k over 3. That's the mass. We're not done with the whole calculation yet by any means. Okay, so the y coordinate of the center, just kidding, the center of mass, y bar, let's put a bar on that sucker, that's going to be 1 over m. Why am I doing that? Okay, 1 over m, and we just calculated that, so that's good, times the integral over the same setup, that's a good thing. We don't have to change the setup every time, even though we do different integrals. Of y times rho. Now y is r sine theta. Okay, just kidding. It's not working here. There we go. R sine theta times that kr again. So don't forget, all that stuff still goes in there. Yeah, I didn't mean to do that. Okay. There we go. So r d theta is the dA. Kr, which is rho, times that turns it into a dm. This is the little bit of mass. And then we use that as a weighting to multiply times the function, which is y, but that's r sine theta now. Okay, so I'm just going to leave this as a 1 over m for a minute. So now it's not just theta gives us a pi, but we can still separate it out into two pieces. That's integral 0 to pi of sine theta d theta. And then the k is coming out. That's going to cancel pretty soon. And then the integral 1 to 2 of, now it's r cubed dr. Okay, so the k over m stays. Integral 0 to pi sine theta is 2. That's a really easy calculation, I won't do. And then integral 1 to 2 of r cubed, that gives us r to the 4th from 1 to 2. And let me go ahead and put the m in. So I got 2k and r to the 4th over 4. Just kidding. Don't want to forget that. R to the 4th over 4. So actually the k goes in the bottom. Let me just leave the m in for 1 sec. And then r to the 4th, 16 minus 1 is 15. Okay, so now let's put in the k. Put in the m, rather. Okay, so 1 over m is 3 over 7 pi k. I forgot to check this in the back of the book before I did this, and I'm doing it in a little bit of a hurry. So we'll see if we get the right answer. So we get 45 over 14 pi. And bear with me for a sec while I check, because I don't want to put up something that's false, or, well, I'd have to redo it is what I'd have to do. And 45 over 14 pi. And that's the y coordinate, and of course the x coordinate is 0. Done.